So for topic 6 on page 26, we want to figure out how efficient an object is that's, for example here, a large electric motor, 90% efficient at transferring the energy from electric energy to kinetic energy. A light bulb, so we're talking maybe like an incandescent bulb down here, where we're converting electric energy to light energy, 5% efficient. So we need to be able to do some calculations with this. And no machine is 100% efficient. Why can't we have 100% efficient machines?
Because there's always going to be friction and
energy loss to heat, sound,
Yes.
light.
Yep. Yep. So whenever we've got particles moving, we're going to generate some heat. And in the operation of machinery, yes, sound, and it could also be light as well. So we know that we can't make a 100% efficient machine. But a lot of engineering is to do with improving the efficiencies of equipment. So if you've got a piece of equipment that's operating at 75% efficiency and somebody can tweak it to get 80% efficiency out of it, then that can save businesses heaps of money. So that's why they employ mechanical engineers. Okay, so if we look at our worked example on page 27, we have here a dog team of huskies that's pulling a sled with a total force of 2,800 newtons. So we have a sled and we've got dogs. There's supposed to be 2 of them, but that's as good as I can get with the dog. And so we've got 2,800 newtons of force. It says after they have pulled on the traces for 25 meters, the 200 kilo sled is moving at a speed of 6 meters a second. So our initial velocity is 0. Our final velocity is 6 meters a second. The mass of the sled is 200 kilograms. And we want to calculate the efficiency. So this 2,800 newtons is what the dogs are doing. Okay, this is the force of the dogs. We know that the mass is going to be the mass and acceleration of the sled is going to be in the opposite direction, isn't it? And so that's what we need to find out. Firstly, and it's 425 meters. So work is equal to force times displacement. Because we're calculating energy, which is in joules. And we know that we've got this work energy relationship where we're both measured in joules. So you can use any of the formulas on your formula sheet. Just because it says it's work and not energy doesn't matter. Because we do know that the work is equal to the change in energy. So we have 2,800 newtons multiplied by the 25 meters. So this is how much? 70,000 joules. That's the work done by the dogs. And but what did we see from the sled? I'll do it over the sled. Okay, so that was the dogs. This is the sled. Well, we were able to take the sled from no kinetic energy when we started out all the way up to having our kinetic energy of, it's going to be a half times 200 times the velocity squared. I don't know why it says 62 there. 6. Can you put that away? Because that's not right. Beg your pardon?
Accidentally turned the torch on there.
Why is it on the table in the first place?
Just in case.
Okay, so the answer is correct in the booklet where it says 3,600 joules. But what's 6 squared? 36, and it has written in your booklet 62. I have no idea
I
why.
think the 2 didn't like go up the top of the 6. They're probably like,
Ah, you're right. It should have been good thinking. So the energy efficiency then is our output divided by our input multiplied by 100 to make it a percent. Okay, we should get rid of that percent symbol in the booklet because that's just wrong. So it's 3,600 divided by the 70,000 multiplied by 100 gives us 5.1%. Now just say you do these two calculations and you can't remember which way around to put them, which one goes on top. If you get this one around the wrong way, you're going to have an efficiency far, far greater than 100%. And that won't make sense. So you'll be able to see that you've got them around the wrong way.
So back on the previous page, it says the heat pump has 250 to 370 efficiency.
It says you can't have, sorry, it says on the previous page.
Page 26.
Yeah, so for the heat pump, it says it has 250 to 300% efficiency.
Yeah. So a heat pump is working by exchanging heat from basically, if you're using it as an air conditioner, it's taking the heat from the room and moving it outside. And yes, they are quite efficient at that process. The more modern ones, it involves using carbon dioxide gas and heating and cooling of the gas on either side of the room. And it's a better version, if you like, of a fridge. Like modern fridges are also basically heat pumps. That's why it's always warm at the back of your fridge, and if you buy a fridge, they tell you that you can't put it completely enclosed into the cupboards in the kitchen. There has to be ventilation so that the heat can dissipate from the back of the fridge. Yeah, they are particularly efficient under certain circumstances. So, for example, they are the most efficient operating, say, between 20 and 25 degrees because they haven't got a lot of work to do. But if outside's 0 and you're trying to use it to heat your house, it's actually not going to be as efficient as that because there's got a big temperature difference to try and to modify. Okay, time to do some questions.